Okay. All right. So for the recording's sake, this was our system. This was our system of equations. Our objective function z, our constraints, of which there were 4. x1 is greater than or equal 0. x2 is greater than or equal 0. I made the mistake here. This is x1 minus x2 is greater than or equal to 3, not equal to 3, greater than or equal to 3. And x1 plus 2x2 is less than or equal to 6. Okay, so I will correct the slides. That was my mistake. Okay, so those systems of constraints led us to a graphical depiction of a restriction on the x1 and x2 values we could have. Okay, and intuitively, the maximum z value has to occur somewhere on the edge of that figure. Particularly, it has to occur at one of the corners, where one constraint meets another constraint in terms of limiting our values. So we just computed where those corners were by solving systems of equations of each pair of constraints, and then calculating z. And in this case, we just wanted to pick the z with the biggest value. Okay. All right, let's look at another system of another linear constraint problem. There you go. I even had that on the slides. So my cheat, graphical depiction of x1 and x2 space. Okay. Hopefully that looks like close to what I have. Maybe a little less colorful than mine, but also probably a little less scratchy. Okay. There we go. All right, so let's take now a word problem, convert that into a linear optimization problem, and then solve the linear optimization problem in order that we can solve the word problem and really make a good decision on whatever it is it's asking us. So the word problem is a calculator company, a company making calculators. They make scientific calculators and graphing calculators, so 2 kinds. Okay. Long-term projections indicate they can sell at least 100 scientific calculators and at least 80 graphing calculators each day. So that's how many the stores can sell. Okay? Because of limitations in production, right, they can't make an infinite number of calculators. They can only make 200 scientific and 170 graphing calculators each day. Okay? So that's just how much machine time, person hours they can afford. Okay? To satisfy a shipping contract, they have to ship at least 200 units a day. So the combination of graphing and scientific calculators has to be 200 or greater, or the shipping company won't work with them. They won't ship their calculators. Okay? Now, assume that each scientific calculator sold results in a loss of $2. That is, it costs $2 more to make it than sell it, unfortunately. But graphing calculators give a profit of $5 each. Okay? The question is, how many scientific and graphing calculators should we make each day, okay, to maximize profits? Okay? So we're going to take that description of a problem and turn it into a linear optimization. Okay? So what we're trying to achieve, our objective, is profit. We want to maximize. Okay? I'm going to write that as profit equals, okay, and we have 2 things we can decide, 2 variables. How many scientific calculators we make, how many graphing calculators we can make, okay. So I'm going to represent that, okay, with a science, SCI, and a graph, GRA, okay. So for every science calculator we make, we lose $3, okay? So we're going to multiply that by -3. For every graphing calculator we make, right, we make $5. So profit is -3 times the number of scientific calculators plus 5 times the number of graphing calculators. Sum that up. Okay? That's how much profit we will make. That's what we want to maximize. Okay? So we're going to have a space represented by how many scientific calculators and how many graph calculators we can make. Okay. But we have constraints. Right? One of our constraints says that the number of scientific calculators we make, right, must be greater than or equal to 100. Okay. Another constraint says the number of graphing calculators we make must be greater than or equal to 80. That is, those are the base amounts we're going to sell. Okay. We also are limited in how many we can produce. So the number of scientific calculators we can make must be less than or equal to 200. The number of graphing calculators we make must be less than or equal to 170. Okay? So those are production constraints. So we have sort of our marketing constraints, how many we want to sell minimum. We have our production constraints, how many we can make maximum. Okay? And then finally we have a shipping constraint that says the number of scientific calculators plus the number of graphing calculators must be at least, that is, greater than or equal to 200. Okay? Okay, so that's what we have. So our profit is our objective. We want to maximize this. It's computed as scientific calculators times -3 plus number of graphic calculators times 5. We have 5 constraints. Okay? All right. So let's start graphing these constraints. So I'm going to represent these first 2 constraints in red. Okay? The number of scientific calculators must be greater than or equal to 100. So we'll say that's 100 right there. You can't go to the left of that line. Okay? Number of graphing calculators must be at least 80. So we'll represent that by that line. So we have to be somewhere in this space here, according to our red. Okay? Okay? Let's take our production constraints. We'll represent those with the blue lines. Okay? The number of scientific calculators has to be less than or equal to 200. Now, I'm not going to make this to scale. Okay? So we'll make this 200. We'll make this 200. And we'll make this 170. Okay? So not to scale. This isn't 0, 0 necessarily. Okay? We have to be above and to the right of the red lines. We have to be below and to the left of the blue lines. Okay? But now we have one more constraint. Luckily, I have one more color. Green. Okay? The scientific calculator number plus the graphic calculator number must be greater than or equal to 200. Okay? So theoretically, if we wanted to sell the minimum of 100 scientific calculators, right? So we can't go past that, to the left of that. We want to sell at least 100 scientific calculators. We would have to sell 100 graphing calculators as well, right? Because 100 plus 100, right, would be 200. We have to have at least that many. Now, the more scientific calculators we sell, right, the fewer graphing calculators we could sell. Does that make sense? So we can sell up to 200 scientific calculators, at which point we could theoretically sell 0 graphing calculators and still make our minimum. Okay? Or likewise, if you sold less than 100 scientific calculators, we would have to sell more graphing calculators. Okay? And this is greater than or equal to, so we need to be above the green line. So now we've limited ourselves to that space there. It's almost a square, except it's got one corner chopped off by the green shipping constraint. Okay? So we can't go below the green line, can't go below or to the left of any red line, and we can't go above or to the right of any blue line, which means we have 5 possible corners. Okay? Everybody with me? All right. So 5 possible corners where constraints meet up, where we know, by definition, the maximum profit has to be. Okay? Because again, any profit represented out here in the middle, you could always get a better profit by either going up, more graphing calculators, or left, fewer scientific calculators. Right? Profit would go up. So in general, we want to go either up or to the left, moving that direction. Right? Is the best profit. Okay? So probably the best profit is going to be here, intuitively. Most graphing calculators, least scientific calculators. Okay? But let's go ahead and solve for a couple of these points so you can see how it works, and we can confirm. Okay? Let's solve for the worst one first. We think the worst one is probably down here. That is the most scientific calculators for which we lose money, the least graphing calculator for which we make money. So what is this point here? Well, this point's pretty easy to solve because it's a vertical and a horizontal line. It's 80 graphing calculators, 200 scientific calculators, right? So this point down here is 200 scientific calculators, 80 graphing calculators, for which we can compute profit, right? Somebody want to do that for me? Negative 600 plus 400. Negative $200. I think that's right. Okay. So definitely, probably not where we want to be. Okay. We're losing money. Let's try one of these. So let's look at this point here. This is where a red line, the minimum of 80 graphing calculators, meets the green line, the shipping constraint. Okay. So it's pretty easy to compute what that point is. We know the graphing calculators is 80. We know the scientific calculators, in order to get a minimum of 200 shipping, would have to be 120. Okay? So this point here is 120 by 80, okay, for which we can compute profit. So 120 times negative 3, negative 360. 40? Positive 40? Okay. So I'm going to take your word for it. Positive 40. Okay. So we can lose $200 at this point. If we move to this point, we would make $40. Okay. Let's go ahead and solve for this one. So again, this one's easy to compute because we're on one of these red lines here, which is a hard cutoff, right? This is saying the scientific calculators must be greater than or equal to 100. So we know the scientific calculator amount here is 100. The number of graphing calculators would be governed by the green line. So if scientific calculators is 100, graphing would have to be 100, right? So 100 and 100 of each, which means we'd make $200, right? So this corner, we lose 200. If we move to this corner here, we make $40. If we move up the green line, as far as we can go, we'll get to $200 profit. Again, intuitively, we think our best profit's going to be up here. So let's see. This profit says we need 100 scientific calculators and 170 graphing calculators. Right? Now again, the two constraints that are binding us here is the minimum number of scientific calculators and the maximum number of graphing calculators. It's more than enough to meet the shipping constraint. That is, we're not on the green line up here. We're not even close to the green line. So we don't have to worry about, it's not constraining us at that point. What's constraining us is a minimum scientific calculator count and a maximum graphing calculator count. So let's see, what would the profit be here? 850, 550? So a profit of $550. Right? And we can compute this pretty easy since we know what it is. 201.70. And it's what? 250. Okay. So as our intuition would have told us, maximizing profit occurs in this corner of the constrained space. And we maximize profit by building the minimum number of scientific calculators we could, 100, and the maximum amount of graphing calculators we could, 170. But recall, we did all that by looking at this word problem, describing a situation from which we deduced or sort of wrote the constraining equations and the objective equation. And then we just figured out where do those constraining equations meet up and which one of those meeting points gives us the best profit, the best objective. Okay. One more? Let's do one more. They're not easy yet, are they? Not too easy, I hope. All right. All right, you need to buy some filing cabinets. You know that cabinet X costs $10 a unit. It requires 6 square feet of floor space, so that's how wide the base is. And it holds 8 cubic feet of files. Cabinet Y costs more, $20 per unit, requires more space, 8 square feet, but holds more files, 12 cubic feet. You've been given $140 for the purchase, though you don't have to spend it all. Okay, so it's not a hard constraint, it's a less than or equal to constraint. The office has room for no more than 72 square feet of cabinets. How many of each model should you buy in order to maximize storage volume? Okay, so we have 2 things to decide: how many X cabinets to buy, how many Y cabinets to buy. So I'll just use X and Y. Okay. Our objective we want to maximize is storage volume. Okay. And storage volume is, well, if every X cabinet gives us 8 cubic feet, then 8 times X, the number of X cabinets, plus 12 cubic feet times Y, number of Y cabinets, gives us how many cubic feet of storage space we'll have. Right? So that's our objective, volume, 8X plus 12Y. Okay? So we're going to create a space, X and Y, that's going to be constrained in some way. Okay? So what are our constraints? Well, first we have a price constraint. Right? So every X cabinet costs 10. So 10X. Every Y cabinet costs 20, plus 20Y, must be less than or equal to 140. And it's been more than $140. And it's been $10 for every X cabinet, $20 for every Y cabinet. Okay. We also have a constraint on the square feet. So every X cabinet takes 6 square feet, 6X. Every Y cabinet takes 8 square feet, 8Y. That must be less than or equal to 72, number of square feet we have. Okay. Okay. So our objective is volume. I'm going to graph this space here in a second. We have so far 2 constraints. There's actually 2 more constraints, okay, which are non-negative. You can't buy negative X cabinets for negative volume and negative square feet, right? So by definition, X has to be greater than or equal to 0. Y has to be greater than or equal to 0. Okay. easy enough. So, easy enough, we can't go below or to the left of this graph. Got to stay out here in this space. Okay? So let's graph these. All right, easy enough. 10x plus 20y is less than or equal to 140. Okay? So we can rewrite that as y, we messed it up, y less than or equal to, okay, 7 minus 1/2 x. Does that make sense? So, minus 10x on each side, so we have 140 minus 10x. 20y must be less than or equal to that. So if we divide both sides by 20, we have y less than or equal to, well, 140 divided by 20 is 7. 10 divided by 20 is half. So 7 minus half x. Y is less than or equal to 7 minus half an x. Okay? So when we get to an x of 14 from a y of 7, that's our limit. Right? So y less than or equal to 7 minus half x would look like this red line here, and obviously less than, we're going to have to be below it. Okay? So when x is 0, when we have 0 x cabinets, right, then we have to have less than or equal to 7 y cabinets. Okay? If we had, let's say we had 8 x cabinets, we would have to have 7 minus half of 8, or 7 minus 4, and y would have to be less than or equal to 3. If we had 14 x cabinets, we'd have to have 0 or fewer y cabinets. Okay? So that's our constraint. Let's do the floor space equation. So again, let's just write this as y is less than or equal to, okay? So 72 would have to divide by 8. Okay, so 9 minus, okay, so far, okay, 3/4 x. Okay. So that's the second, the floor space equation. 6x plus 8y less than or equal to 72 can be rewritten as y must be less than or equal to 9 minus 3/4 of x. Okay. So again, we can graph this. So there's 9. 3/4 of 9, yeah, okay, somewhere there, right? It's not it's not a whole value. It's going to look something like that. Okay. So we have a green line representing our floor space constraint. We have a red line representing our budget constraint, how much we can spend. And then obviously values have to be positive anyway. And so we effectively have 4 corners if you want to count 0, 0. But really three points at which we could theoretically maximize volume. Okay? Let's do the easy one first. So this point up here represents no x cabinets. So x is 0, y is 7, right, according to our budget constraint. So this value here, we have 0 x cabinets, we have 7 y cabinets, and the volume, right, for that is 84 cubic feet. Let's solve for that point there. So that's where the green line and the red line meet up. So let's figure out where would the green line and the red line meet up. Well, we have a green and red equation here. Okay, so we can solve for one and just put the value in for the other. basically we're going to say, where do these two equations equal each other? That is, where does this y equal this y, which means 7 minus half an x equals 9 minus 3/4 an x. Okay? So we can move stuff around algebraically and come up with 1/4 of an x equals 2, which means x equals 8. Does that make sense? So I took the green and red equations, system of two equations, two unknowns, two equations. You could solve, input one for the other, solve for x. So x is 8. Okay. If x is 8, 7 minus half of 8 is 3. Right? So y is 3. Same thing you can say here. 9 minus 3/4 of 8, 9 minus 6 is also 3. Right? That's the point. It's where these two equations meet. So x is 8, y is 3. It's where those two equations meet. And the cubic space would be, so 64 plus 36, 96? No, 64 plus 36, 120? You sure it's 120? It's 100. Okay. I think 120 is on it. 64 plus 36. 100 square feet, or cubic feet.
Yeah.
And then lastly, so this point here, now the easy thing is it's the green line. It's where y cabinets equals 0. Okay. The question is, when y equals 0, what would x equal here? Okay. So basically 3/4 of an x is equal to 9. Okay. So what? 36, 12? I think that's right. So 12 x cabinets, 3/4 of 12 would be 9. 9 minus 9 would be 0. So that's where the green equation technically meets y is greater than or equal to 0. Okay. So 12 x cabinets, so 8 times 12 would be 96 cubic feet. Had a feeling there was a 96 somewhere. Found it. Okay. So these 3 points. Now this one's easy too. 0 and 0 equals 0 cubic feet. Right. So technically, that could be our best. If we were minimizing volume, hey, the best way to do that is to buy nothing. Right. Easy enough. We knew the maximum volume had to be somewhere along these 3 points. Okay? It turns out it's in the middle here, which makes sense. Right? If I drew a theoretical line from those 2 edge points, one to another, right, I could bump out a little bit to get to this other point out here where the red line and the green line allow for some distance, right? So intuitively, it makes sense why that is our best point, right? We can increase x and y more than these 2 base values would allow us in between them. So we can get out, and we find that we will buy 8 x cabinets, 3 y cabinets, okay, to maximize volume. Now, out of curiosity, do we also use all our budget? Without doing the math, could you tell me if we use all of our budget? And why? Remember, our budget here is represented by the red line. Right? Are we on the red line or below the red line at that point? We're on it, right? It's the point where the red and green lines meet. So we're on the red line, which means we're at our we're hitting the limit of our budget. We're staying at the limit of our budget, in addition to the limit of our floor space, right? That's what the intersection of the green and red lines there mean, is that we're using all of our budget and all the floor space we have available in order to maximize the volume of storage we would have. So without even looking at, well, would 8 and 3 equal 140 spending, you could just look at that and say, well, yes, that budget constraint is limiting us. We would go past it if we could. We're right at it. So yes, we're using all our budget. And yes, we're using all of our floor space because it's limiting us. We would go past that green line, but we were told we can't. So we went right up to it. Okay. Obviously, these two constraints, the fact that we have to buy more than, or can't buy less than 0 X cabinets or less than 0 Y cabinets, isn't really a limiting factor when we're trying to maximize volume. Because volume only goes up when we buy more X or buy more Y. So those weren't a strict limitation. Okay. Any questions about linear optimization problems? So here's the good news. I will not give you a linear optimization problem with more than 2 variables. That's good, because otherwise you end up with combinations of 3 variables, 3 equations to solve, and it's impossible to draw that anyway, right? You have to draw 3D. It gets hairy, very ugly. I won't ask you to ever do that by hand, okay? Now, next week we'll look at how we use Excel in the Analytic Solver platform software to solve linear optimization problems of 3 variables, 4 variables, 10 variables, right? It can do it very easy. And the reason it can do it so easy is because intuitively, when you look at the graph, there's very little to solve, right? All you have to do is solve a couple systems of equations to find those points at which one constraint meets up with another and another, or whatever, however many variables you need, okay? So that's all it has to do, okay? There's an infinite number of possible answers inside that octagon or whatever shape it ends up looking like. But we know the best value for our objective will always be on an edge somewhere, and will always be at a corner somewhere. So all we have to do is find the corners and figure out which one's the best. Okay? So a computer can do that literally milliseconds, no problem. Okay? So we'll do that next week. So that takes care of tonight. So we learned about data mining, very quick whirlwind tour of data mining. Okay? 3 algorithms. We learned about solving linear optimization problems by hand. Okay? Pretty quick, but fairly easy. Okay?